Ever wonder how much power you can actually pack into a tiny space? I mean, from the fuel in our cars to the batteries in our phones, we're always dealing with just one fundamental concept: energy density. It's kind of the secret ingredient that decides what's possible and what's still just science fiction. So let's dive in and see what's really powering our world. And, what might power our future.
Oh yeah, science fiction absolutely loves this idea. We've all seen it, right? These tiny, impossibly powerful energy sources. Like powering a time machine with just a banana peel and a beer can? The Mr. Fusion from Back to the Future is the perfect example. It's the dream of getting pretty much infinite energy out of a device the size of a coffee maker.
So the big question is, how close are we, really, to packing that much of a punch? Well, to answer that, we've got to get into the real-world physics of storing energy. We're going to go on a journey, starting with the familiar stuff and ending up with the fantastically powerful, all grounded in the actual science of what's possible.
Okay, so first things first, what exactly is energy density? Well, put simply, it's all about how much energy you can cram into a certain amount of stuff. It's all about the packing.
Now, there are two key terms we're going to be throwing around. First is specific energy. That's how much energy you get per kilogram of mass. Think of it as energy per pound. Then you've got energy density, which is energy per liter of volume. Think energy per gallon. For most of what we're talking about today, we're going to focus on specific energy. It's just the best way to do a fair apples-to-apples comparison to see what's really the most powerful, pound for pound.
All right, to really get a feel for the numbers here, let's start with things we use every single day. This is going to give us a baseline, a sort of measuring stick, so we can appreciate the truly mind-blowing scales we're about to get into.
Okay, right off the bat, you can see a massive jump in power. A really good lithium-ion battery, like the best we have, stores maybe 1.8 megajoules per kilogram. Dry wood, one of the oldest fuels humanity has ever used, stores about 10 times more than that. And then you have gasoline, which basically doubles that again to around 42 megajoules per kilogram. And this, right here, is the fundamental challenge for things like electric cars. A single kilogram of gasoline packs over 20 times more energy than a kilogram of our best batteries. That huge gap is why a tank of gas can take you, say, 400 miles, while a battery that weighs the same might only get you 20. It's why chemical fuels have been king for over a century. So the main takeaway here is, even in our normal world, the energy gaps are just enormous.
But chemical energy? That's just the beginning. The first truly massive leap in our ability to store energy came when we figured out how to unlock the power inside the atom itself.
Okay, get ready for a giant jump. The specific energy that was let loose by the nuclear fission in the Trinity atomic bomb was 19,000 megajoules per kilogram. Seriously, just let that sink in for a second. 19,000. That is not a typo.
Let's put that into perspective. Gasoline, our best everyday chemical fuel, is sitting there at 42. Nuclear fission is at 19,000. That is a jump of more than 450 times. 1 kilogram of that nuclear material has the same energy as a convoy of 25 tanker trucks filled to the brim with gasoline. We are talking about a completely different scale of power.
And this is where we leave the world of conventional tech behind and start stepping into the frontiers of physics. The kind of stuff that sounds like it was pulled straight out of a sci-fi movie. You see, scientists are actually looking into even more exotic ways to store energy. Things like metastable nuclear isomers. You can think of them as atomic nuclei that are kind of charged up, holding on to extra energy like a tiny wound-up spring. Then you've got degenerate matter, which is the super crushed stuff you'd find in the core of a dead star. And of course, the theoretical holy grail of energy storage, matter-antimatter annihilation.
And look, these aren't just made-up concepts from a movie. The source material for this is a serious scientific survey, and it explicitly looks into these bleeding-edge ideas. They're theoretical for sure, but they are absolutely rooted in the known laws of physics.
And if you could actually harness that, well, this is the kind of energy you'd get. 90 times billion megajoules per kilogram. That's the power you unlock when you convert mass completely into energy, just like in Einstein's famous equation, E equals mc squared. It's a number so huge it's almost impossible to wrap your head around. It makes the power of a nuclear bomb look like a tiny little firecracker.
But if you want to find the true champions of energy density, you have to look beyond anything humans could ever hope to create and look out into the cosmos, to the most extreme objects in the entire universe.
As incredible as antimatter is, nature has it beat. And to even talk about these cosmic objects, we have to switch gears, from energy per kilogram to energy per liter. And why is that? Well, the forces involved are so extreme that matter gets crushed into impossibly small spaces, so volume becomes the only meaningful way to compare them.
So check this out. This is the estimated energy density of a stellar mass black hole. That number you're looking at is a 6 followed by 27 zeros. It's the energy that is locked inside the event horizon of a collapsed star, a concentration of power so unbelievably immense, it's beyond human comprehension.
And now for the grand finale. What's the ultimate energy density? Well, scientists call it the YLEM, or the cosmic egg. It's the theoretical energy density of that single point from which the Big Bang and our entire universe just exploded into being. This, for all intents and purposes, is the biggest number in physics. It is the absolute limit.
So, from a simple little battery all the way to the birth of the cosmos, we've basically just climbed a ladder of power that spans more than 170 orders of magnitude. And these aren't just abstract numbers. They represent the fundamental limits of what energy can do.
And that brings us right back to our original question. We might not have Mr. Fusion just yet, but the universe is clearly packed with incredible power. Our journey, from figuring out simple chemical bonds to understanding these cosmic forces, really shows how far we've come. And it leaves us with one final thought. If we could safely and controllably tap into just the next step on this ladder, what would our civilization be capable of? What would our future even look like?